All right, thank you everyone for coming to the Graphs and Matroids seminar. Today our speaker is Daniel Bernstein, who will be talking about symmetry-forced rigidity in the plane.
All right, well, thank you, Rose, for inviting me to speak, and thank you all for being here. Before I get started, I just wanted to, first say, since I know there's a lot of people in the audience who are at LSU, that next year I'm going to be at Tulane. So keep me in the loop on any Louisiana-related Matroid theory stuff. And then also, I recently wrote a guest post on the Matroid Union blog that sort of talks about the basics of algebraic matroids in rigidity theory and matrix completion, which, if you find this interesting, that will go into some more of like the basics around this area. And I'm not assuming any background in anything other than Matroid theory, so I don't worry if you are not familiar with that blog post. But yeah, so anyway, just to get started, the very basic sort of fundamental definition in rigidity theory is that of a bar and joint framework. And all that is a graph where you've just specified locations in d-dimensional space for your vertices. For example, here are three frameworks in the plane in R2. They're all on the same graph. This is just the 4 cycle. And I've just indicated here where I've positioned the vertices. So, and frameworks, they can be rigid or flexible. And what I mean by this is you imagine that your edges are rigid bars that are free to move around the vertices. And with this in mind, the whole framework itself, it can be rigid or it can be flexible. So looking at this square on the left here, it's flexible because I can sort of shear this top edge back and forth and deform the structure. With this one, there's a similar deformation. You can think of sliding this diagonal-ish edge back and forth. But if I were to do something obnoxious, like put vertices 1 and 2 at the same point, the resulting framework would then be rigid. Now, and the way matroids come into play here is that rigidity is a generic property of a graph, in the sense that if you fix a graph and then just say, all right, let's look at just a generic way to stick the vertices into d-dimensional space, then either you're always going to get something rigid or you're always going to get something flexible. So for example, if I take a 4 cycle with a chord, this is generically rigid in the plane, because if I just slap the 4 vertices down without trying to break things, like say this or like this, you can just hopefully intuitively kind of see that this is a rigid thing. I can't do that same sort of shear that you saw in the previous slide.
Excuse me, Daniel.
Yeah.
Someone's asked, saying that the light in the background is distracting. I don't know if it would be too dark if you turn it off or anything.
Yeah,
but...
I can turn that off. Yeah, hold on, let me, yeah. Is that better?
Yeah, looks good. Thanks.
Okay, sorry about that. So yeah, I'll say that a graph is generically rigid in RD if for every generic way of sticking the vertices into d-dimensional space, the resulting framework is rigid. And I'll say that such a graph is minimal if removing any edge destroys this property. And so just, I mean, I'll get to this more precisely, but the graphs that are minimally generically rigid in RD are the spanning sets of a certain matroid. The graphs that are minimally generically rigid are the bases of some matroid. And I should say, by the way, please stop me at any point with questions. I have no problem being interrupted.
And I'll let you know if someone says something in chat.
Ah, great, thank you. All right, so here are some classical results. The sort of, big overarching question is, which graphs are minimally generically rigid in RD? And it is a focal or proposition that you can probably see intuitively that a graph is generically rigid in R1 if and only if it's connected. So for example, with this graph on the left that's disconnected, you can sort of wiggle each connected component of this back and forth on the line independent of the other. And that is a deformation of this. But as soon as you connect the two components, well, then now the whole thing can only move as a unit. So, keeping in mind that rigid graph, so the spanning sets of some matroid. The content of this is that this rigidity matroid in one dimension is just the graphic matroid. In two dimensions, there's also a characterization. It's due to Hilda Polchek-Geiringer, but that was evidently forgotten until like 1970 when Gerard Lemon claimed to have proved this. But anyway, the characterization is that a graph G is minimally generically rigid in R2 if and only if it has 2 times V of G minus 3, or twice the number of vertices minus 3 edges, and every subgraph on some number of vertices has at most twice that number of vertices minus 3. And just the way to think about this intuitively, all right, this is characterizing minimal generic rigidity. The first condition says you have exactly the right number of edges. We know this is a matroid, so it's always going to be the same right number. And the second condition just tells you that they're not all just bunched up in one spot. They're sort of spread throughout the graph. And characterizing generic rigidity in 3 dimensions is like the major open problem in rigidity theory. And there aren't even that great conjectures for what the characterization should be. But in this talk, I'm going to focus on symmetry-forced rigidity. And in this setting, the idea is that you have some symmetry constraint on your framework. And this comes up in a lot of applications, which I'm not going to get into. But the idea is you only now care about flexes that preserve the symmetry. So for example, this framework, it has symmetry with respect to a wallpaper group that just has your a translation to the right, a translation up, and a degree 4 rotation. I claim that it's symmetry force flexible. In other words, there exists a flex of this framework that preserves this symmetry. And this you can see in this animation, which I'll make a little bigger. So yeah, this, as you can see, at every point in this animation, the symmetry is still preserved, but the framework is flexing. Okay, and so sort of the main kind of big problem in symmetry-forced rigidity is just to characterize generic symmetry-forced rigidity in RD. And I'll go through this a little bit more precisely in terms of what that means. And by the way, this is like this thing on the right, this gadget on the right, this is a gain graph. And this is going to describe the symmetric framework modulo of symmetry. I'll get to that later, or right now, actually. So given a group S, a graph G has S symmetry if there exists a free action of that group on the vertex set such that the action of each element is a graph isomorphism. So either that was a trivial statement to you, or you have no idea what that means. Either way is fine. Let's just look at this example. This is a simple concept that's just difficult to sort of state without it looking confusing for the first few times, but it's easy to see in an example. This graph is symmetric with respect to the cyclic group of order 4. And you can just see, and just intuitively what that means is if you rotate it 90 degrees, it looks the same. So that intuition is sufficient for this talk. Now, symmetric frameworks can be compactly represented with gain graphs. I imagine a lot of people in the audience are familiar with this. Maybe a lot of people also aren't, but so given a group S, an S gain graph is a directed multigraph G whose arcs are labeled by elements of that group S. And I won't go through the full sort of formal details about how a gain graph specifies a symmetric graph, but the idea is that your vertices of the gain graph correspond to vertex orbits of your symmetric graph. So this, if you think about this, order 4 rotation, there are 2 vertex orbits, right? When I rotate this 90 degrees, the black vertices wind up at black vertices and the white vertices wind up at white vertices. And the arcs of the gain graph correspond to edge orbits of the symmetric graph. And the way you assign arcs and gain labels to them from the symmetric graph, it involves an arbitrary choice. You begin by choosing some representative of each vertex orbit. So I'll choose the circled black vertex and the circled white vertex as my vertex orbit representatives. And notice I have in the gain graph representation here an arc labeled a squared, where a is the 90-degree rotation from the white vertex to the black vertex. And what this means on the level of the symmetric graph is that if I apply the group element a squared to the white vertex, I'll move, or the representative from the white orbit, I will move from here to here. And that gives me something adjacent to the chosen representative of the black orbit. And the self loops correspond to the fact that some of your your edges connect vertices within the same orbit. So does the idea of gain graphs and symmetric frameworks make sense? Does anyone want further clarification? Have any questions? Okay, so with this in mind, the main problem in symmetry-forced rigidity is for each dimension D and each subgroup S of Euclidean isometries of RD, characterize the S gain graphs that are minimally generically rigid. So again, this means they have no flexes that preserve the symmetry, or in other words, all flexes break the symmetry. So just to give you a brief sort of history of work on this problem, the mathematical foundations of it were laid out in two separate papers, one by Baron Schulze and Walter Whiteley in 2010, and a different one by Borchardt Stranu in 2010. The Schulze and Whiteley paper focuses on the case where your group is finite, or a point group. And then the other paper is where your group is a lattice. And since then, there was sort of this like brief kind of flurry of activity to just sort of characterize symmetry-forced rigidity in various special cases of the group. Yeah, the references are all here in case you want to go back and look at it. I'll mention some of these as they come up. But what I'm going to talk about is a sort of generalization of parts of a lot of these previous results. And what's kind of what I find exciting about this is sort of the proof strategy. It uses tropical geometry, but it also uses, I guess, to me, what feels like some actual matroid theory, and not just using the word matroid, from submodular function theory, and in particular, a construction that associates a matroid to any submodular function. But yeah, so I'm going to talk about of symmetry-forced rigidity for a particular class of groups, namely groups that preserve orientation. So before I get to that, I just need to define a few more terms related to gain graphs, which again, if you're familiar with them in the context of matroid theory, this is probably a review. So the gain of a walk in a gain graph is just the product of the labels in that walk, but you invert whenever you traverse an arc backwards. So and a balanced cycle is a cycle whose gain is the identity. I am being a little abusive with the notation here because a cycle by itself is not a walk. I didn't specify a starting point in a direction, but let's just look at an example. So if I were to take the walk around this cycle, say clockwise, starting at this vertex, it will be A times A inverse times R inverse, which is the identity. And this is why it doesn't matter that I'm being abusive with the notation here, because it turns out that if I start at any vertex along this cycle and go any direction, I will always get the identity. And if I were to take, say, a non-balanced cycle, so this cycle, this triangle here, I claim is not balanced. For example, if I start at this vertex and traverse clockwise, I'll get R inverse AR. Which is not the identity in this group, the dihedral group. If I were to start at a different vertex, if I were to say start here and also traverse clockwise, I would get gain label A. Now A is not the same as R inverse AR, but they're both not the identity. And that's really the only thing I care about with the, well, yeah, I mean, that's all you need to define balancedness of a cycle. Okay, so that's what it means for a cycle to be balanced. And just two other definitions that I need just before I state the theorem and then start talking about the proof are not, or okay, this first one is maybe not so familiar. Okay, so a bicyclic graph, okay, this is familiar. It's a subdivision of one of the following graphs. And I will say that a bicyclic gain graph is Dutch if each pair of closed walks based at the same vertex have gains that commute. And the other definition I need is just that of a complete gain graph. So Kn of S, complete gain graph on n vertices with gain group S. It has vertex set 1 through n, and it's going to have an arc between every pair of vertices for each element of the gain group. And it's going to have a loop at every vertex for each non-identity element. So here's the simplest example, K2 of Z2. It's this gain graph. For the one pair of vertices, I'm going to have a arc for each element of the gain group. So I have an arc labeled 0, I have an arc labeled 1, and I'm going to have a loop at each vertex for every non-identity element in the group. There's only one, so there's only one arc at each vertex, and that's the complete gain graph. So here's the theorem. Let S be a subgroup of the semi-direct product of R2 and SO2. So this is just Euclidean isometries that preserve orientation, or in other words, Euclidean isometries where when you try to represent it as, you know, AX plus B, A has a positive determinant 1. But anyway, so it says, okay, for each S gain graph H, I'm going to define alpha of H to be 3 if every cycle in H is balanced, 2 if not, and the gain of each cycle is a translation, 1 if none of the above, and all bicyclic subgraphs are Dutch, and 0 otherwise. So then G is minimally generically infinitesimally rigid in R2, if and only if the number of edges is twice the number of vertices minus alpha of the complete gain graph on that group. And for all subgraphs, you have the same equality, but with an inequality. And note, this should remind you of the theorem I had a while ago on generic rigidity in 2 dimensions, the Polacek-Geiringer result, sometimes called Lemans theorem, which was exactly this, except instead of alpha of stuff, it had 3. And so yeah, this is the theorem. I'm going to talk about the sort of the ingredients of the proof next. And I'll talk about a few like sort of simpler intermediate results that you can use some of the proof techniques for. And in particular, I will now formally define like the matroids that are actually coming into play here. Before that, does anyone have any questions? Okay. Yeah, and I should say next up, hopefully we'll see, one thing I'm working on with people at the Fields Institute now is to try to extend these proof techniques to accommodate reflections. Yeah.
Actually, I do have a question, maybe just because it's taking me a second to like look and see it at this alpha. I guess the question is, what does it mean that the gain of each cycle is a translation?
Right. So the group consists of Euclidean isometries. So Euclidean isometries, or sorry, direct Euclidean isometries that are orientation preserving. So this is a rotation followed by a translation. So what I mean by the gain of each cycle is a translation is just that rotation is trivial. There is no rotation, it's just a translation.
Great, thank you.
Any other questions?
A less important question, but why Dutch?
Why Dutch? Oh, yeah. So some people call bicyclic. So hey, here, let me go back to the definition of Dutch. Some people call bicyclic graphs bicycles or bicycles. And the condition of being Dutch is a condition about gains commuting. And at least in the US, bikes designed for commuting are called Dutch bicycles. So that's the, yeah.
Wow.
I was very proud of that. Yeah, any other questions? Okay, yeah, so I'm gonna skip that example. Actually, it's not that illuminating. Okay, just to give you a sketch of the proof, the idea. So as I alluded to before, at least in the non-symmetric case, the graphs that are S symmetry-forced rigid are the spanning sets in the algebraic matroid of a variety I'm going to define called the S-symmetric Haley-Menger variety. I'm going to define all of these terms, so don't worry if any of these you don't know. When the group of isometries is orientation preserving, this is something called a Hadamard product of affine spaces. So a Hadamard product is just a really simple way of taking two varieties and turning them into a new one. I will explain that too. And this allows you to use a lot of matroid theory to understand what's going on. So in particular, so each affine space, it defines two matroids, one of which is an elementary lift of the other. I'll get into that later more precisely. But what that enables me to do is to describe the algebraic matroid of a Hadamard product of affine spaces in terms of these two matroids for each affine space. And the proof of this uses tropical geometry. And then I apply that formula I come up with in this setting. And it involves a particular lift of the gain graphic matroid of a complete graph, or sorry, of a complete gain graph. And so this is sort of a big picture of what's going on here, and I'll get into more details. So yeah, so yeah, if you're lost before, you should be able to come back in now with no loss of clarity. Here is a definition. So again, I just, by the way, I'm going to use this notation. You know, if E is a set, C to the E denotes the complex vector space whose coordinates are indexed by elements of E. In this case, every subset S of E, it defines a coordinate projection just onto that subset of coordinates. By variety, I just mean a subset of C to the E that's cut out by a bunch of polynomial equations being zero. If you don't know what irreducible means, don't worry about it. Now, if V is an irreducible variety, a given subset of the coordinates, I will say, is independent if the dimension of the projection onto those coordinates is the number of coordinates. In other words, if the corresponding coordinate projection is full dimensional, and I'll say, you know, it's spanning if the dimension of the projection of that variety onto those coordinates is the dimension of the original variety. And of course, it's a basis if it's both independent and spanning. And okay, these are, I'm actually using these words in the matroid theoretic sense. These are the independent spanning sets and bases of a matroid. And just one quick sanity check you can do is if you let V be a linear space, then if you take a matrix whose rows span that linear space, then the column matroid of that matrix is exactly the algebraic matroid of that variety. I think probably the first question on any matroid theorist's mind is, well, are these representable? We're working over C, so the answer is yes, all of these are actually representable. If you were to, you know, define the same construction over finite fields, the answer would be no. But since we're working over characteristic zero and in uncountable fields, these are all just representable matroids, but they're coming presented in a certain way. And just for another, you know, non-linear example, if I let E just be the set of entries of a 3x3 matrix, and if I let V be the variety of 3x3 matrices of rank at most 1, then I claim that this set of entries is spanning but not independent. And so if you look at the projection of the variety of 3x3 matrices of rank 1 onto these coordinates, there's 6 coordinates here. and they satisfy one equation, so this set is 5-dimensional, I claim that the variety of 3x3 matrices of rank at most 1 is also 5-dimensional, so this is a spanning set. It's not independent because the projection is not 6-dimensional, and I have 6 coordinates I'm projecting onto. So are there any questions on the definition of an algebraic matroid of a variety? All right, so what does this have to do with rigidity theory? Well, in the non-symmetric setting, these rigidity matroids are the algebraic matroids of this variety called the Cayley-Menger variety. So given a pair of integers, d and n, the Cayley-Menger variety of n points in Rd, which I'm going to note this way, is just the affine variety embedded in c to the n choose 2 as the Zariski closure of the set of possible squared pairwise Euclidean distances between n points in Rd. So don't worry if you don't know what all of the words in that definition mean. Here's an example. So if d is 2, the ijth coordinate of the Cayley-Menger variety of n points in 2 dimensions is just going to be this. So it's going to be the distance between 2 points in the plane. Or rather, yeah, and I guess just to sort of say this same thing again in a different way. The idea, you have n points sitting in d-dimensional space. You take their pairwise distances between them. This gives you 1 point in c to the n choose 2. Now, do this process for every collection of n points in d-dimensional space. This gives you some set in c to the n choose 2. Now take the Zariski closure of this set, and what I mean by that is just look at all the polynomial equations that vanish on this set that you swept out, and then just throw in all the other points that also vanish at those polynomial equations. So this gives you some variety. It's irreducible, I claim. And what's important about this is that the algebraic matroid of this is exactly this rigidity matroid that I sort of alluded to in the beginning. And what I mean by that is a graph G is generically rigid in d-dimensional space if and only if E is spanning in the Cayley-Menger variety of endpoints in d-dimensional space. Moreover, G is minimally generically rigid if and only if E is a basis. And just to sort of intuitively see why this is not surprising, what does it mean for a graph to be flexible? Well, that means that if you sort of fix distances between pairs of points by sticking a rigid bar between them, it's flexible means that you can sort of change distances between other pair of points that don't have a bar between them without, bending any of your bars or breaking or whatever. Now, if you sort of look at what's going on in terms of pairwise distances among all your points, this gives you a curve that lives inside your Cayley-Menger variety. Now, I claim, okay, so this is flexible. I claim that means you're not spanning, because if you were spanning, then the fibers of your projection of your Cayley-Menger variety onto the distances specified by your edges are going to be 0-dimensional. In other words, once you fix those pairwise distances, there are only finitely many things, there are only finitely many ways you can sort of fill in the remaining distances. But if you're flexible, in other words, if you have a curve in your Cayley-Menger variety that satisfies all your distance constraints, well, then that's infinitely many points. So it's just sort of the intuitive idea there. Yeah, any questions about that, by the way, before I go on? Okay, so where'd my cursor go? All right. So I'm going to skip this slide. Now, okay, so that's matroids from varieties. So another way that you can get a matroid that I'm interested in is from a submodular function. So if f is an increasing submodular function, in other words, it satisfies these two conditions, I'm going to define the matroid associated to that function to be the matroid on ground set E, where a subset is independent if and only if for non-empty subsets, the cardinality is less than or equal to that function. So there are many examples of this construction. Maybe the most, I guess like the first interesting example of this construction is if you take the rank functions of D matroids all supported on the same ground set, then I is independent in the matroid defined by this function you get, this function you get by summing them, if and only if I is a union of independent sets in one from each of the matroids. In other words, the matroid defined by summing up all of these rank functions is just the union, the matroid union of those matroids. Now, this construction interacts very nicely with something called the Hadamard product of varieties. So given 2 points in the space f to the e, I'll say the Hadamard product of those 2 points is just the coordinate-wise multiplication of them. And so the terminology comes here from, so like a Hadamard product of 2 matrices is just, if you have 2 matrices of the same side, you just like do exactly what you would tell your undergrad linear algebra students not to do, and just sort of coordinate-wise multiply things together. You can define this just sort of arbitrarily in points, get a Hadamard product. The Hadamard product of 2 varieties is just what you get when you sort of take, pair of points from each of your 2 varieties, take their Hadamard product, and take the Zariski closure of this set that you get. Another way to think about it is it's just like Minkowski sum, except instead of taking sums, you're taking products, and then Zariski closure. So here's a theorem. If U and V are linear spaces, then the algebraic matroid of their Hadamard product is just the matroid you get using the submodular function construction, where your submodular function is just the sum of the rank functions minus 1. Yeah, the proof of this uses tropical geometry, and just to sort of give you a vague idea of why. So in tropical geometry, products become sums. So the and I know I'm losing a lot of people here. I will come back, so don't worry if you're lost here. The Hadamard product, the tropicalization of a Hadamard product is just the Minkowski sum of tropicalization. So this just gives you a very nice sort of like a thing you can do to make sense of things. But anyway, so now to apply this to something rigidity theory related. Okay, so I'm done using tropical geometry words. The Cayley-Menger variety of endpoints in endpoints in 2-dimensional space is the Hadamard product of some linear space with itself, where that linear space is spanned by the incidence matrix of the complete graph on n vertices. And so applying what we know about the rank function of complete graphs, in the graphic matroids, this tells us that if R is the rank function of the graphic matroid underlying Kn, then the algebraic matroid underlying the Cayley-Menger variety of endpoints in 2 dimensions is just M of twice R minus 1. And this, this goes back to Lovash and Yamini in 1982. They proved this using just combinatorial means, but there's a deeper geometric reason behind this, which is this. And it generalizes this symmetry-forced setting to an extent. Okay, so how are we going to apply this kind of reasoning in a symmetry-forced setting? Well, we need a variety whose spanning sets are the symmetry-forced rigid graphs. So, okay, fix your, let S be a group of Euclidean isometries of Rd. I'm going to abuse notation a bit and write F to the Kn of S to denote the F vector space with coordinates indexed by the arcs of the complete gain graph. I'm going to define this map that takes a set of endpoints in d-dimensional space to this vector space whose coordinates are indexed by the arcs of this complete gain graph in the following way. I will say that the d of some point at a particular arc is just going to be the squared pairwise distance between the point on the source of the arc minus the gain of that arc applied to the target. So, okay, I do this across all sets of endpoints in d-dimensional space. This gives me some set in C to the Kn of S. The risky closure of that set is what I'm going to call the symmetric Cayley-Menger variety. And so, as it turns out now, that an S-gain graph, G, is generically infinitesimally rigid if and only if it's spanning in the algebraic matroid of this symmetric Cayley-Menger variety. Here's an example. If S is the group generated by this matrix of an order 2 rotation, here's my complete gain graph on 2 vertices with that group. D of 2 points in 2-dimensional space is just what I get when I take every pair of points and then every gain label, and then just look at the distance between one of the points and then that gain applied to the other vertex. So for example, here is what I get for one of the loops. So this is, I take my first point, x1, y1. This is the distance between that and the thing I get when I apply this matrix to it. This arc, this entry corresponds to this arc. It's the distance between x1, y1 and x2, y2. This entry corresponds to this arc. It's the distance between x1, y1 and A applied to x2, y2. And then this is the entry corresponding to this arc. It's the distance between x2, y2, and then A applied to x2, y2. Okay, so now I have the variety whose algebraic matroid I need to understand. It turns out that when the group that I'm interested in is orientation preserving, in other words, everything is just rotation and translations, okay, then the elements of this group, they just, okay, there's a translation and then a rotation. If I do the following change of parameters, then the entry of this variety corresponding to the arc E, remember, and where E has translation part AB and rotation part this, the entry of the Cayley-Menger variety corresponding to E is going to be this product of these two affine forms. And from this, it follows that this variety is just a Hadamard product of affine spaces. So I know some of the details here are probably not going to sit so solidly, but really the point of this is that when I assume that my group is just consisting of translations and rotations, then I apply some change of coordinates. And then once I do that, under that parameterization, the variety I care about is very clearly a Hadamard product of affine spaces. And I should say something similar happens when S has reflections, but it's just complicated enough that it messes up the combinatorics and you can't use like submodular function theory. But anyway, okay, so this motivates now, I need to understand what the Hadamard product of two affine spaces look like. And then once I do this, I have a formula for, I have a way to understand rigidity of symmetry-forced rigid things, provided my group doesn't have reflections and I'm in the plane. And so here's that. So I'm going to think of an affine space as parameterized as just, the column span of a matrix plus some vector. Now, the algebraic matroid of an affine space is just the row matroid of A. I'm going to define a lift of this matroid to just be the row matroid of AB. So I'm just concatenating B as the last column of A and looking at the row matroid of that. So ML, it turns out, is an elementary lift of MV. And what this means by definition is that a set I is independent in the algebraic matroid MV. That implies that I is also independent in this lift. Okay, and so with this in mind, I'll let U and V be finite dimensional affine spaces. I have to put that here because E can possibly be an infinite set. I'm going to define this function on the subsets of V as follows. I will say f of S is just the sum of the two ranks of S in each of those two matroids if either, or if the rank increases in the lift in either of those two affine spaces. So yeah, U and V are both affine spaces. I can look at the rank in its algebraic matroid, and I can look at the rank in the lift. If it increases going to the lift in one of these, then the rank of S is going to be this. And then if it doesn't, I'm just going to subtract one. And then with, armed with this function, I can just say now that the matroid of a Hadamard product of affine spaces is just the matroid you get defined by this submodular function. It's submodular, it's increasing, so we can apply that construction of Edmonds and get a well-defined matroid. That's the algebraic matroid of this Hadamard product. Okay, and this is, yeah, okay, so now that I have this formula for the Hadamard product of two affine spaces, I just need to apply it to this symmetric Cayley-Menger variety. And this winds up in nicely with gain graphic matroids. So, which, is maybe familiar to a lot of people in the audience. So, so the gain graphic matroid of a gain graph G is the matroid supported on the arc set of G, whose independent sets are sets of arcs such that each connecting component has at most one cycle, which is not balanced. For example, if your group is just this group generated by an order 4 rotation, okay, so for example, this cycle around the outside, this square around the outside, that has gain identity. So that would be a dependent set. But if I were to say have this path that goes like this, and then add this, sorry, no, that's not the right example. Sorry, if I were to take, if I were to take, if I were to take this cycle going counterclockwise, starting from here, that would be an independent set. Oh, sorry, and then adding this arc, that would be an independent set. It has a cycle, but the gain of that cycle is A, so it's not balanced. Okay, so now why am I introducing this? Well, okay, so I already claimed that the Cayley-Menger variety in this symmetric case, when S doesn't have reflections and I'm in the plane, I claim that this is a Hadamard product of two affine spaces. And it turns out that these affine spaces, they have the same algebraic matroid, and it's just the gain graphic matroid of the gain graph obtained from this complete gain graph, but I'm just ignoring the translations. And then the corresponding lifts are obtained from the gain graph of this by declaring that non-Dutch bicyclic subgraphs are independent. And so depending on how familiar you are with like the language of elementary lifts, my like cyclic, so yes, I take this gain graph, I ignore translations, my, what is it, like the linear class of circuits whose rank is going to stay the same now are just the, like, I guess, balanced subgraph, or sorry, these are going to include the Dutch bicyclic subgraphs, and it's also going to include balanced subgraphs that remain balanced when I add the translation part back. But anyway, yeah, so just applying all of those formulas and stuff together gives the result, which I'll just state again here. I guess I won't read through it again because all these details probably take a minute to settle in. But there's a theorem. That's where it comes from. And I guess that's all. So I will take questions now. Thank you all for your attention.
Awesome, thank you. We have not been doing pause at the end. I know that kind of sucks, but it's hard to time everyone to do it all at the same time. So, but yeah, now's a good time for questions. If anyone in the audience has any questions, I'll get started with something kind of easy, which is that I'm wondering if there's just any interpretation of the dual of the rigidity matroid.
Dual of rigidity matroid. Let's see. Huh. You know, I should have seen that question coming, and I don't have a good answer. The dual of the rigidity matroid. I mean, I guess your co-circuits of the rigidity matroid are going to be sets such that if your graph is rigid, you have to have like some edge from that set. I'm trying to think of it. I don't know if there's a great like intuitive. I mean, there probably is. I don't know of a great intuitive interpretation of that off the top of my head.
I've got some other questions, but I'm liable to embarrass myself asking some of the questions about rigidity and algebraic matroids. So first of all, are there any other questions someone wants to ask while we're still recording? All right, and let me